Hello, my name is John Bannon. I'm an attorney and philosopher. Today, I want to tell you how you can prove that the universe is superdeterministic through time dilation. Now, when I talk about superdeterminism, I'm talking about a particular version of superdeterminism that was proven by Swedish theoretical physicist Dr. Johan Hansen in 2020. So Dr. Hanson's version of superdeterminism says that we live in a predetermined static block universe without cause and effect in physics. You can find his proof in the journal Physics Essays, volume 33, number 2, 2020. So, in addition to his proof that the universe is superdeterministic, there's another way you can show it through Einstein's relativity, specifically time dilation. So, uh, cause and effect in physics describes the relationship between physical phenomena where one event, the cause, leads to another event, the effect, due to the interactions governed by the laws of physics, resulting in a change in the properties or state of the affected entity. Time dilation is a phenomenon in physics, specifically in Einstein's theory of relativity, where time passes at different rates for observers who are in relative motion or who are in different gravitational fields. Now, time dilation has absolutely been experimentally verified to be true. And it's also been shown to affect the radioactive decay rates. The rate of radioactive decay has been also experimentally verified to be inherently random. So, decay rates are a quantum effect, and that effect has been shown to be inherently random, which means it doesn't have a prior deterministic cause or trigger to make it occur. It's what's known as a form of acausal physics. So you can research the fact that decay rates can be affected by time dilation and that they're inherently random for yourself. Just look for the muon experiments. So, uh, in this proof, this experiment, this thought experiment, take two equally weighted samples of a radioactive element like cobalt 60. So, for instance, let's say we have two equally weighted, uh, isotopically identical blocks of a radioactive element like cobalt 60. Now, if we measure the decay rate in each of these blocks using a Geiger counter, so each block gets its own Geiger counter, we can count the number of decay events uh, during any period of time for each block. So if you take one block with its Geiger counter, and let's say you put it in a spacecraft and you shoot it out into outer space at an extremely high rate of speed, and you put it in an elliptical orbit around the sun so that it's constantly moving at a very high rate of speed for a fairly long period of time, this would cause time dilation because of the relative velocity of the cobalt in the spacecraft compared to the other cobalt that remains stationary on Earth with its Geiger counter. So, what you'll discover is that after about 7 years or so, you will see a statistically significant change in the decay rate, or the number of events of decay in this cobalt block as compared to this one, which stays on Earth. And what happens is, because this is moving at a higher relative rate of motion compared to this block, its rate of decay slows down relative to this one. So what you end up with is, after about 7 years, when you count the number of decay events, you'll discover that this sample orbiting the sun has significantly fewer decay events than this one. What has happened is the rate of decay, radioactive decay, for this sample has slowed down relative to this sample due to time dilation. Um, and this is all true. So this is just an experiment you could perform, but we know what will happen because it's already been experimentally confirmed with muons, as well as Einstein's theories of relativity say this as well. So what you have essentially, after 7 years, when you compare the decay rates of these two samples of cobalt 60 is a radioactive element, you have two seemingly identical blocks that are no longer identical, because the one that was orbiting the sun now is isotopically dissimilar to the one that was stationary on Earth, because this one has had fewer decay events in it compared to this one. So they're no longer physically the same, exactly the same objects. This one's different than this one. Now, they are different, but you have to ask yourself, what caused this sample to be different now than this sample? There was no physical interaction between these blocks. There was no physical interaction with this sample orbiting the sun with any physical object that could account for the fact that now this object is different than this one, even though they are originally the same. So what caused this object to be dissimilar to this object? Well, it was the passage of time, because time slowed down relative to the object on Earth. For this object orbiting the sun, that decreased the decay rate for this object. And when you bring them back together after 7 years, there's a noticeable physical difference between these two objects due to the passage of time. So the change in the rate of the passage of time for the one object due to time dilation is the only cause for the difference that you now see between these two objects 7 years later. Now, this is very, very important. And the reason is this: because the decay events in cobalt are inherently random quantum events, that means they are uncaused events. That means they don't have a prior deterministic cause that results in the decay event. So they're uncaused events, which means that the rate of change in the decay rate for cobalt is also an uncaused event, because the rate of change is based on the number of decay events that occur over time. And if the decay event itself is uncaused and not caused by a prior physical interaction or trigger, then the change in the rate of decay has to also be uncaused. What does this mean? Well, it means that because the only thing that could cause the change in the rate of decay for this cobalt orbiting the sun was the slowdown in time, then time itself has to be an uncaused thing, because time caused this uncaused change in the differences between these two cobalt blocks. So what does this say? This says that the idea that the present moment of time causes the next moment of time has to be wrong. Because if the present moment of time causes the next moment of time, then there's no way the present moment of time could cause the next moment of time in which the decay rate of this cobalt block it has been slowed down because the process of decay rate is itself uncaused. So the passage in time, in order to cause the change in the decay rate, can't be a causal process, which means the present moment of time cannot cause the next moment of time. In order for this phenomenon of time delay to affect uncaused decay rate changes in a radioactive block like cobalt 60. So if the present moment of time cannot actually cause the next moment of time, then that means the next moment of time must already exist. Because we know it arrives, but if it's not caused to come into being by the present moment of time, the only way it could arrive is if it's already there. And the only way it could already be there is if there is a hidden fourth dimension of time. So this shows that we have to live in a predetermined static block universe without cause and effect in physics. In other words, we live in a present moment of three-dimensional space within a larger block universe that has a fourth dimension of time. So I hope you enjoyed this, and I'll give you a moment to look at what I've written on the board so you can absorb it. But the end result is cause and effect in physics is not real, and we do live in a predetermined static block universe without cause and effect in physics. All right, take care.